Thank you very much for the introduction, and most of all, thank you very much for the invitation. I'm going to present results which are joint work of Sergio Kleinerman, but I'll start with some introduction of what is actually the black hole stability problem. And let me even start with something more basic, which is the presentation of the main equations in this talk, which are the Einstein equations in the vacuum. So I'm going to start with a Lorentzian metric M, which has dimension 4, 1 for time and 3 for space. And that comes together with the Lorentzian metric G, which has signature minus, plus, plus, plus. So let me immediately present the simplest setting, the simplest case, the simplest example. So this is the Minkowski spacetime. So the manifold is R1 plus 3. And the Minkowski metric written here in Cartesian coordinates is given by minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. Okay, so as I said, I'm going to consider the Einstein vacuum equations. So that is the Einstein equations in the vacuum, in the absence of matter, in which case they take the following simple form. Ricci is equal to 0, where Ric is the Ricci tensor of the metric G. So the metric G admits a curvature tensor. It's a 4 tensor that contains all the information on the curvature. And the Ricci tensor is a trace of this curvature tensor, so it has only partial information on the curvature. And this is in fact a system of equations, because Ricci tensor is a 2 tensor. So this equation here, it's a symmetric 2 tensor in dimension 4, so it amounts to 10 equations. Okay. So in general, these equations, if you write them, so you can write them in any coordinate system. That's what is called general covariance. So general covariance means that the laws of physics should not depend on the particular coordinate system. So you can write the Einstein equations in any coordinate system, which means that when you consider a solution, you don't consider a single solution, but a class of equivalence of solutions modulo diffeomorphism. In other words, whenever I have a metric, I can cook up another solution, which is just the metric written in the different coordinate system. Okay, so this will be important later in the talk, but it is also immediately relevant because I can write the Einstein equation in a specific coordinate system so that you can see how they look like. So here, let me just warn you beforehand that I'm going to use a coordinate system on this slide, which I will not use again later in the talk. It's just for the purpose of showing you one example, one form of the Einstein equation. Okay, so if I write them in a specific coordinate system called wave coordinates, doesn't matter how they are defined. This is the analog of harmonic coordinates of Riemannian geometry. Then you see that you get the following system of equations. So what is this system? First of all, it's a system on the metric components. So G alpha beta denotes the metric components of your coordinate system. And D'Alembert G is the D'Alembert in the metric G. So it's the generalization to a curved, to a Lorentzian manifold of the standard D'Alembert of Minkowski that you know. Okay, and then on the right-hand side, I have some coupled nonlinearities. Okay, so this is a system, and of course I'm in dimension 4, and the metric is symmetric. So this means that this is a coupled system of 10 nonlinear wave equations. And in fact, they are quasi-linear because even the top order derivatives are nonlinear, since the D'Alembert depends on the metric. Okay, so this is a system of 10 quasi-linear wave equations. In particular, this is clearly a hyperbolic system. So again, bear in mind that you have the freedom of choosing coordinates. So in a different coordinate system, they will look differently. So you should not take it too seriously. What you should take seriously is that this is a hyperbolic system of equations and that it is nonlinear. Okay, so the evolution problem, so since these are wave equations, this is a hyperbolic problem, and therefore there is a Cauchy problem involved, or an evolution problem. And we know since the seminal work of Choquet-Bruhat and later Choquet-Bruhat-Garrosh that there is local existence and well-posedness for this system. In other words, if I take sufficiently smooth initial data, the Einstein vacuum equations are locally well-posed and there exists a unique maximal solution. Okay, so this introduction is meant to just to say that since it's an evolution problem, I can consider in particular the evolution of specific initial data, and the kind of initial data we'll consider are perturbation of well-known stationary solutions. So already on this slide, there is one stationary solution. This is the Minkowski spacetime. The Minkowski spacetime has a Ricci tensor 0, and in fact, a Kerr tensor 0. So this is a particular solution of the Einstein vacuum equation. And in fact, the causes that I will mention today started exactly with looking at the simplest stationary solution, which is the stability of Minkowski. So I'm going to look at stability of stationary solutions, but I'm going to look at more complicated solution than Minkowski, which is the trivial solution of the Einstein equations. I will look at so-called stationary black holes, and let me introduce them now. So there are Kerr, and so the more general family is the Kerr family of black holes, and it will have, I will single out a particular case of this family, which is the Schwarzschild solution, which would be a subfamily of the Kerr family of metrics. Okay, so what are first the Kerr metrics? So again, I have the freedom of coordinate system. So let me pick a simple one, which are called Boyer-Lindquist, which is simply TR theta phi, so spherical coordinates. In these coordinates, I can write the Kerr matrix as follows. So this is a complicated expression, and I don't intend you to remember it. It's in fact, I also don't remember it. Usually I have to look it up. The only important thing here is that obviously I could write it down. So this is an explicit solution. Number one. Number two, it's a family. There are two parameters, A for angular momentum and M for mass. So it's a two-parameter family of explicit solution, although checking that it's a solution, it would be quite difficult, except that nowadays we can use a computer. And finally, the third information is that if you look at all metric coefficients here, which are expressed using these functions here, they do depend only on R and theta coordinate. So in particular, they do not depend on the time coordinate t, which means that the solution is stationary. So it's indeed a stationary solution. And in fact, it also does not depend on phi, which means that it's also axis symmetric. There is an axis of symmetry. Okay, so then let me, since I will also mention it, let me mention the particular case where you take the angular momentum 0. So if you take A is equal to 0, this complicated formula drastically simplifies, and you get the following solution, which are the Schwarzschild metrics, which historically were found, in fact, much before the Kerr metrics, because they are much simpler, and in particular, spherically symmetric. So this formula is also not relevant for the talk, except, in fact, for the next slide. So let me mention the last point that I want to say, the last thing I want to say about Kerr and Schwarzschild, which is, in fact, the main point, is that these explicit solutions are contain, in fact, a black hole. So how do you see that? So this is my next slide. So first of all, let me say that Schwarzschild spacetimes, which correspond to angular momentum 0, are in fact correspond to non-rotating black holes, while Kerr is the more general case of rotating black holes. And in fact, for Kerr, let me mention that you have to restrict the angular momentum to be less than the mass in absolute value. Okay, so now since the way to see that you have a black hole is similar for Schwarzschild and Kerr, let me do the particular case of Schwarzschild, which is simpler to explain, even though it's I mean, because of the simpler formula. Okay, so now let me go back to the formula for Schwarzschild. So first of all, let me remind you that Schwarzschild, we have seen it's spherically symmetric. So for simplicity, I will simply draw things in the TR diagram. So each point of this diagram is in fact a two-sphere. Now, if I come back to this formula, you see that the coefficients 1 minus 2m over r here and there in front of dt square and dr square, they converge to 1 as r goes to infinity. And once they have converged to 1, at the limit, you recover the Minkowski metric written in spherical coordinates. So that means that these metrics are asymptotically flat. And in fact, for Kerr, it would be more difficult, but you can also check it's true. So these metrics are asymptotically flat, which means that as r goes to infinity, they look like Minkowski. However, when r becomes smaller, of course, this becomes very different from 1. And in particular, there seems to be a singularity at r is equal to 2m here. Okay, so here, in fact, it's not a true singularity, which means that if we remember that there is general covariance, I can always change coordinates. And this is, in fact, a coordinate singularity. I can remove it by a change of coordinates. But nevertheless, this hypersurface r is 2m has a special meaning, which I will draw here. Okay, so in this diagram, I draw the light cones of Schwarzschild. So when r is very far, very large, as I said, you look like Minkowski, so you have the standard light cones that you know. And then the more you move towards small values of r, the more you differ from Minkowski. And in fact, what happens is that these light cones will tilt to the left. And so, yeah, that's the left. It's so much to the left that when you arrive at this boundary R is equal to 2m, they are completely tangent to it. Okay, in particular, the light cone here points inwards this hypersurface R is equal to, it points inwards R less than 2m. So you can never, even light, because light is constrained to light cones, the light cannot escape from that region. Okay, and that's exactly what is called a black hole. So that means that R less than 2m is the black hole because any light cone, any light emitted from there cannot escape. And this the boundary of your black hole, R is equal to 2m, is called the event horizon. Okay, so I claim that you have exactly the same picture for Kerr, but let me not do it. It's easier to draw it to do it on Schwarzschild. Okay, so now I can state, now that we have seen that I presented this stationary solution, let me quote, let me state the black hole stability conjecture, which in fact is another name for the stability conjecture for the Kerr family. Okay, so here recall that we're in the context of asymptotically flat solution. As we have seen, these are asymptotically flat solutions. They look like Minkowski for large R. And these are asymptotically flat solutions to the Einstein vacuum equations. And the conjecture is as follows. So first of all, this is the conjecture. This is not the stability of the whole space-time. It's just the stability of the exterior of the black hole. Okay, in fact, the interior of the black hole is believed to be unstable. It's conjectured to be unstable. It's also a very interesting problem, but here I'll stick to the exterior and therefore to the stability conjecture of the exterior region of the black hole. Okay, so you start with small perturbations of your initial condition corresponding to Kerr with the restriction that the sub-external restriction, the absolute value of the angular momentum is strictly less than m. And then you expect that the solution will be global, stay close to Kerr, and converge to another Kerr solution at infinity. So in other words, you have asymptotic stability, but you will converge to a different member of the family. So for a different final angular momentum and final mass than the one you started with. Okay, so let me immediately, before starting, continuing with the history, explaining the history of this problem, let me immediately mention a particular case which started the program, even though it's quite different in spirit, because I'm going to start with Minkowski, which does not have a black hole. But nevertheless, formally, if you take m is equal to a is equal to 0 in the Kerr form, in the formula of Kerr, you formally get back Minkowski. Therefore, even though Minkowski does not, of course, it's a singular limit because Minkowski has a different topology. It doesn't have a black hole, but nevertheless, it's interesting to see that it is formally part of the family, and therefore the first stability result was indeed obtained for Minkowski, and this is a monumental work due to Chris and Kuhlmann. But let me mention that this is it has a different topology. So this is why you can actually talk about the stability of Minkowski without talking about stability of Kerr. In other words, if you start close to Minkowski, you converge to Minkowski. You don't converge to another Kerr member. This is why this could be done first if you want. Okay, so now let me, to get more insight into the problem, let me discuss what is called the linearized relative system, which is nothing but the linearized system around Kerr. So you look at the linearized equation around your stationary solution. So here, let me remind you, you're looking at the quasi-linear system. So obviously, it's a vastly simplified toy model problem, but nevertheless, it gives you interesting information. And the problem for the linearized solution of the linearized problem is to prove that they decay, let's say, at a sufficient rate to have the hope to use it for nonlinear problems. So this problem was started in the 60s and 70s in what is called the golden age of black hole physics. There is a vast literature devoted to the subject. So first, let me discuss what you get in the particular case of Minkowski. In the particular case of Minkowski, even though you start with a complicated nonlinear system, the linearized system drastically simplifies and you just get one scalar equation. And in fact, it's one wave equation on Minkowski. Now, in the case of Kerr, this is no longer the case. The linearized system itself is already non-trivial because it's a large and entangled system. It does not decouple. So what was done first in the physics literature was to, in fact, try to find a kind of triangular structure to this system. In other words, find and in fact, do the first step of that triangular structure. So when you have a large coupled system, which is hard to analyze. One way to get around that problem is to try to triangularize it. At least if I had the linear, ODE with the matrix, that's one way to solve it. So you want to triangularize, and of course, to triangularize the system, the first thing you need is to get the upper component of your triangular matrix, which is therefore a component which is diagonal, which means in this context, it means finding a component of the system that totally decouples from the rest. And then you hope to first control that and then control the rest of the solution starting from that. So in fact, Tucholsky exhibited such a quantity at the level of the curvature tensor that satisfies a linear wave equation, albeit not non-conservative. In other words, it does not derive from a Lagrangian. So I'm writing schematically this wave equation here. The fact that it does not derive from a Lagrangian is due to this potential here in red, which will create problem. But at least formally, it allows you to start this triangularization procedure of the linearized system. Okay, of course, in the nonlinear setting, you don't get zero, but you get coupled nonlinear terms. You get quadratic terms on the right-hand side. Okay, so the goal after the work of Tucholsky is to try to prove decay for the scalars psi plus and psi minus, the so-called Tucholsky scalars. And then, starting from there, derive decay for the rest of the solution to the linearized gravity system by precisely exhibiting a kind of triangular structure as I described. Okay, let me, before providing results on the linearized gravity system, let me mention first an obstruction to decay. In other words, you cannot expect to get decay for the linearized gravity system because there are obvious obstructions. So let me mention them. So these obstructions comes from the fact that you don't have one solution, but a multi-parameter family of solutions. Indeed, starting from using the parameter MA, any MA and the diffeomorphism phi of R4, I can cook up a solution, a family of solutions of the following form. I have GAM, which I already know is a solution because it's the Kerr metric. And as I told earlier, you have general covariance, which allows you to cook up for any diffeomorphism a new solution, simply by taking back the pullback of the metric. So if you take back the pullback of the metric, this is the kind of formula, here I will write it in coordinates, this is the kind of formula that you get. In other words, GAM is a solution, but if I compose it with this transformation, it's again a solution. Okay, so now that means because you have a multi-parameter family of solution, that means that if I take variation with respect to the parameter M, A, and the diffeomorphism phi, I will find that all these solutions of the nonlinear problem, once I take the variation belongs to the kernel of the linearized problem. It's automatic as long as it depends smoothly, so I can differentiate with respect to the parameters and I get solution of the linear scalar. Okay, so this is of course a well-known problem. When you have a kernel at the level of linearized operator, then you have to, at the nonlinear level, what you have to do is to use modulation theory. And here, an interesting aspect of this problem is that typically this is done in finite dimension. Here, you have to do modulation in infinite dimension because the set of diffeomorphism obviously has infinite dimension. Okay, so if you want the kernel generated by M and A is maybe more standard, but the one generated by phi is infinite dimensional. Okay, so this was for the obstructions to decay. And now let me come back to the linearized gravity system and provide some results. So here I apologize for not quoting the immense literature on the subject, starting from in fact much simpler problems, which are just one wave equation on Schwarzschild or Kerr. Let me immediately quote the end results if you want, the one that directly apply to linearized gravity system. So first of all, the Tucholsky scalars satisfy a non-conservative linear wave equation, as I said. So it's hard to get to extract decay from it, but at least Whiting in 89 in a seminal paper could show that there are no exponentially growing modes. Of course, this is far from being enough for the nonlinear problem because that doesn't exclude that solutions could be not bounded. In fact, they could grow still polynomially or being bounded. While what you need for the linear system is actually to get precise quantitative decay. So then the solution that was found much later by Dafamos, Holzegger, Rodiansky was to, in fact, use something known as the Schwarzschild transform that transforms solutions of Tucholsky in much better wave equation called Regge-Wheeler, which are Lagrangian. And this breakthrough allowed them, was the starting point for them to control first the Tucholsky scalars and finally the whole linearized gravity system near Schwarzschild. Typically, you want to start with Schwarzschild because it's algebraically simpler. And recently, in 2009, this was extended to the control of linearized gravity system was extending to include Kerr for small angular momentum by two teams, Anderson, Begdal, Blue, and Ma on one hand, and Hefner, Hinz, and Vachi on the other. Okay, so this is what I wanted to say on the linearized system, and now I want to talk about I want to move to the nonlinear problem. Okay, so let me first start with Schwarzschild, and I think from the slides on Kerr and Schwarzschild, it's quite obvious. Schwarzschild is algebraically much simpler. And in fact, as I'll discuss later, even beyond the algebra, there are specific features that make Kerr significantly harder than Schwarzschild. So I want to first discuss Schwarzschild. Okay, but unfortunately for Schwarzschild, you cannot really prove stability of Schwarzschild because unlike Minkowski, Schwarzschild is smoothly embedded in Kerr. It corresponds to the case A is equal to 0. So when you start near Schwarzschild, in principle, you end up, in general, you end up near Kerr. So it's hard to, you cannot talk about stability of Schwarzschild without talking about stability of Kerr in general. So what you have to do is to restrict the class of perturbations, so to force the end states to be Schwarzschild. So the one we chose with Sergio Kleiman is the simplest one, is to restrict to a specific class of symmetry, which does exclude Kerr. I mean, which does exclude the case A different from 0, so you just have Schwarzschild as an end state. Okay, so this, so it's not too important what kind of symmetry class we choose. We chose one which is called axial polarized, and the main, so it's axially symmetric, and there is an additional condition to make sure that you don't get Kerr. And in this class, we could obtain the stability of Schwarzschild. In other words, if you start with perturbation in this symmetry class, small perturbation of Schwarzschild, and you end up close to, you converge to another Schwarzschild. Okay, and let me mention that this result was extended recently, in fact, a few months ago, by Holziger, by Dafemos, Holziger, Rodiansky, and Taylor, to include, in fact, a well-prepared codimension 3 set of initial data. In other words, no symmetry. This is, in fact, the optimal result that you can hope for Schwarzschild if you want to make sure that you don't converge to Kerr. Okay, so this was the case of Schwarzschild, and now let me mention the case of Kerr. So I'm only going to mention the case of Kerr for small angular momentum. The general case is not yet within reach. So the result we have obtained very recently with a joint work with Sergio Kleiman a few months ago is the proof of stability for small angular momentum. In other words, the resolution of the conjecture for small angular momentum. And so if you start close to Kerr with small angular momentum, you converge back to another Kerr. And let me mention some statements that we can obtain and some conclusions we get for the converged solution in particular. You obtain the fact that the space-time have a complete future null infinity. So this is a statement about the fact that if you go along null directions, along light cones towards infinity, you have a nice structure. Let me mention, well, okay, forget about von Diemer's formula. It's maybe not very telling for non-experts, but it has a future horizon. So the space-time indeed contains a black hole. The final mass coincides with what is called the final Bondi mass, and also we extract a suitable notion of quasi-local angular momentum, in other words, a local version of angular momentum on null infinity that converges to the final angular momentum of the spacetime. So if you are not very familiar with this notion, I mean, the only important thing to understand is that these are basically very natural conclusions that you expect if you are able to prove stability of Kerr, if you want. Okay, let me, in fact, make connection with a different problem, which has some analogy and differences, which is the case of a positive cosmological constant. So I can take the same equations, but add a positive cosmological constant to the ancient equations. in which case I also get a stationary solution, although different, which is called Kerr de Sitter. And I can look at the analogous problem of the stability of Kerr de Sitter, and the analog of the problem I'm just describing for Kerr was proved by Hinz and Vashi in a seminal paper in 2016 in this context. So small angular momentum, stability of Kerr de Sitter family. So I should say that these are quite different equations, but if you want, there is a clear analogy between the two problems. Okay, so let me, so in the time, yeah, so in the remaining time, what I would like to do is to present both results, the one on Schwarzschild and on Kerr. So what I'll do, in fact, I'll describe what is common to both. So I'll start with a description of the scheme that in fact works for both. And then towards the end of the talk, I hope to have the time to mention what are the new ingredients in Kerr. Okay, so here is the geometric setup. So let me start before showing you what is the bootstrap region, in other words, the region on which we actually work. Let me start with the converged spacetime, because I want to make you familiar a bit with the setting and with the type of coordinate system, or rather gauges, that are used here. So there are two gauges, or if you want, two coordinate system. So you separate the spacetime in two regions, one that is near the black hole and contains part of it, and one that is far. So there is the exterior region, which is far from the black hole, so in red here, and the interior region, which is near the black hole. So here, for simplicity, because I mean, usually for experts, I would draw a Penrose diagram, but this can be confusing sometimes. So let me, here I'm drawing things simply in the TR diagram. So this is like before, the R direction here, and here the T direction. And here I'm drawing things like they were strictly symmetric. Obviously, it's totally wrong. Schwarzschild is strictly symmetric, but already the perturbation of Schwarzschild is not strictly symmetric, and Kerr is certainly not strictly symmetric, and perturbations of Kerr even less. So of course, this diagram should be taken with caution, with a little bit of caution. Okay, and here, okay, so here there are two hypersurfaces. R is equal to R1. Here is a value where R1 is chosen to be less than the value of the event horizon, so that I'm sure to include the event horizon. Of course, it's just slightly less because I told you that I have instability. It's very close to the event horizon, because if I go too much inside the black hole, it's unstable. But I can go still slightly inside, and the advantage is that allows me to totally avoid the issue of the event horizon, which is a bit tricky. I simply go inside the horizon, so I don't have to worry about that hypersurface. This R is equal to R0 is chosen to be outside of the black hole. Its actual value was chosen to be close to the event horizon in Schwarzschild. In Kerr, we actually decided to take it large. It's actually easier, but the important thing is that it's a fixed value once and for all. And then the exterior region goes to R is arbitrarily large in the exterior region. Okay, so here in the exterior region, you can see that there are, this looks like, so these are 45 degrees line. So here in the picture, I use the light codes of Minkowski. Of course, first of all, in Schwarzschild, it's already not correct. And in perturbation of Schwarzschild, or even in Kerr, perturbation of Kerr, is very not correct. So it's just to give you a sense of how things are foliated. Let's say that when R goes to infinity, this picture is not totally crazy. When R is bounded, it's very different, but it's just to give you a sense. So you foliate the exterior region by outgoing hypersurfaces, which in the case of Schwarzschild are null cone. In the case of Kerr, cannot be null cone. So that's why I'm putting null cone in quotes. It's asymptotic to a null cone in Kerr, but for reasons I explain later, these are not actually null cones. But you know, that's okay if you let me still refer to null cones in quotes. And in the interior region, these quote null cone are ingoing. In other words, it's the opposite direction. And this one enter the black hole. Okay, and last thing, on each of these hypersurfaces, I have a function R, a scalar function R, and that scalar function R intersects these hypersurfaces at topological two spheres. In fact, if I was exactly in Kerr or Schwarzschild, this would be two spheres. Well, in Schwarzschild it would be round spheres. In Kerr already it's not round spheres. And of course, in perturbation of Kerr, these are two-dimensional manifolds, but they have the topology of spheres. So let me for simplicity, call them spheres in the rest of the talks, Okay, so now this is the converged spacetime, but I'm not working with it. What I'm working with is a finite region, which is my bootstrap region. So I'm going to bound this spacetime. I'm working with it's a typical continuity argument or bootstrap proof. I'm working with a finite spacetime. I improve my bounds, therefore I can continue forever, and I converge at the end of the continuity argument, if you want. Okay, so to get a bounded region, I'm going to stop my so-called outgoing null codes, which are not null codes. I'm going to stop them. So I'm going to decide that I do not go to infinity. I will start at the last hypersurface, which I call the last slice. Okay, so you should imagine that this, of course, this picture is not very, it's not this region. This last slice is at an arbitrary large distance. So the red region is gigantic. The blue region is very small. So it doesn't show on my picture, but you should imagine that this last slice is very far. Okay, so here I want to mention this last slice because I want to make sure that it's understood that this last slice completely prescribes my space-time. If once this last slice is chosen, and I am free to choose it, then I initialize this light cones in quote from my last slice in a unique manner. And then I stop at r is equal to 0, and I initialize the ingoing ones from the outgoing ones in a unique manner. So in other words, once this is fixed, the whole spacetime is fixed. So if I want to have a chance to converge to Schwarzschild or Kerr, I need to pick this last slice carefully such that it is, if you want, it tracks correctly. It will be foliated by spheres, and I need these spheres to track correctly the spheres I intend to converge with at the end. So there will be a special procedure on this last slide, which I will explain later. But for now on, let me just say that this is a crucial part of the argument to correctly choose this last slice, to carefully choose this last slice. Okay, and it will be foliated by special spheres, which I will introduce later. Okay, so now let me give the main ingredients of the proof. And again, at this stage, the proof, the structure is the same for the stability of Schwarzschild and Kerr, and it's only later that I mentioned the new ingredients for Kerr, what differs. In fact, here the common strategy, if you want, is the same. So first of all, as I told you, you have a large entangled system. This was true in the linearized system. This is, of course, even more true in the nonlinear system. And to disentangle it, you want to use a kind of triangular structure. Okay, and the first thing you do is you follow what was done in the linearized system, and you exhibit the analog of Tucholsky scalars in the nonlinear problem. You derive the analog of the Tucholsky equation in the nonlinear problem, which now doesn't have 0 on the right-hand side, but is coupled to quadratic terms. But the important thing is that there are quadratic, no linear terms. So it decouples from the rest of the solution at linear level. And then you use the Chandrasekhar type transform to control this so-called Tucholsky scalar for the nonlinear problem. This is a part. In fact, this is one of the most technical part of the proof, and it uses strongly the particular structure of the nonlinear term on the right-hand side, which are the so-called null structure for people familiar with these problems. Okay, then once you have these Tucholsky scalars, you want to reconstruct the rest of the solution. You have a large system, so there are many more components to recover. You want to recover the curvature, the curvature components, the connection components, the gammas or the Christoffel symbols if you want, and the metric components. And you do this again by exhibiting this triangular structure. So you start from the Tucholsky scalar and you control every component one after another. So here you want, let me first describe decay estimates. So in this type of proofs, there are always two types of estimates. You have estimates for low number of derivatives, let's say half number of the derivatives. For this, you expect to prove decay. And then there are estimates for large number of derivatives, for which you want to prove boundlessness of energies, if you want. So let me first describe the decay estimates. So here, for decay estimates, you will solve two types of, you will have two types of equations. You will have transport equations along the generator of the null codes in quotes, which are not quite null codes. in Kerr, in perturbation of Kerr, and you will have elliptic systems of Hodge type on the spheres of intersection. Okay, so either you transport things along the generators of the null cones or the approximate or the asymptotic null cones, if you want, or you solve elliptic systems of Hodge type on spheres. And of course, remember that when you reconstruct the solution, you need to deal with the fact that at the linearized level there is the presence of a kernel. So there are two types of kernel. The one induced by the constant M and A, and the one induced with the choice of the diffeomorphism invariance. So the one for M and A is in fact related to the kernel of elliptic systems of Hodge type, while the other one, the one with diffeomorphism, is related to the transport equations. So for the elliptic systems, the point is to suitably choose M and A, and I'll say something in the next slide. You want to have a suitable choice of the constant M and A, which will converge in the limit to M infinity and A infinity, and the suitable choice is such that you will again deal with the kernel of the elliptic system of Hodge type. And concerning the transport equation, you want to fix the diffeomorphism by constructing special spheres that track the center of mass of the solutions. So I'm coming back to this issue of constructing a special last slice, which consists of a concatenation of spheres. I want to construct spheres which will, in the limit, converge to the spheres of Kerr or the spheres of Schwarzschild, in the particular case of Schwarzschild. Okay, so this I will explain I want to come back to this point in the next slide. And finally, as I said, this was decay estimates, but you also need top derivative estimates or energy type estimates if you want. So for the top derivatives, of course, you cannot use just transport and elliptic systems, because you need to use the hyperbolic structure of the problem, otherwise you lose derivative. So you remember they have a hyperbolic problem, mainly in fact for the curvature components. You use a proof by induction of derivatives. In other words, you use the fact that you already had decay for low derivatives. You do an induction argument on derivatives, and you use energy Moravec estimates for wave equations and the Maxwell-like character of Bianchi identities. So Bianchi identities is a system satisfied by the curvature components, the components of curvature, which has looks a bit like a Maxwell system, which is also hyperbolic. Okay, so here I should say that this induction of derivatives is in the same spirit as the triangular structure. So it's again to exhibit a kind of triangular structure, because again you have an entangled system and you need to disentangle it. Okay. Okay, so I still have some time. Okay, so so now I want to focus on two aspects. I want to finish this talk by focusing first on the issue of the kernel. I want to explain, I will more specifically focus on the construction of the special spheres, which track the center of mass and which have to do with this last slice. And I will also discuss briefly, say something briefly about this constant M and A, which track the other kernel, the one due to the elliptic systems. And then I want to finish by explaining what are the differences in Kerr. In other words, what is new compared, so far this scheme is common to Kerr and Schwarzschild. I want to mention the differences, why Kerr is, there are some new challenges. Okay, so let me start with these special spheres, which we call GCM for general covariant modulated. General covariant because this is to deal with the issue of general covariance, and modulated because, as we have seen, this amounts to modulation. So it's modulation to deal with general covariance, hence the name GCM. Okay, so what is the goal here? If you are converging, so again, I chose coordinate system, or rather gauges, which consist of hypersurfaces on which are foliated by spheres. So these spheres play a central role in the proof. And in particular, if you want to converge to Kerr, I want these spheres to converge to the spheres of Kerr in the limit. If you want, these are the spheres that you could see in the coordinate system. When I wrote the Kerr metric in the coordinate system T r theta phi, these would be the spheres of constant T and R. And in the particular case of Schwarzschild, this would be simply round spheres because Schwarzschild is spherically symmetric. Okay, so these spheres that I construct in my perturbation space, in my perturbed space-time should converge to Schwarzschild, so I have to pick them very carefully. Okay, so we have, in fact, we had the first construction in the Schwarzschild paper in 2000. In the Schwarzschild result, we had the first construction in the Schwarzschild result in 2018, but this construction was in fact using the special symmetry that we had. So we later in 2019, we came up again with Sergio Kleinemann, we came up with a construction which is general. In other words, it works for general perturbations, in other words, without symmetry. And it works, of course, also in perturbations of Kerr. Okay, so this procedure, so what is the goal? You want to design have a procedure that constructs a unique two-parameter family of preferred codimension two surfaces. And so these are not exact spheres, these are topological two spheres. So why a unique? A unique because, as I said, I want to converge in the limit to Kerr. So there should be some uniqueness in the way I pick them. Otherwise, I will have a problem. So I want some uniqueness, some rigidity in the construction, if you want. So this construction of this has some analogies, if you want, at least on a physical level, with some well-known celebrated construction of Huisken and Yao, where on three-dimensional Riemannian surfaces, where they construct a preferred family of codimension 1 surfaces. But here in our case, we are in dimension 4 in a Lorentzian spacetime, and it's very important to have a codimension 2 construction, which is actually harder. And codimension 2, because as I said, these spheres corresponds to the spheres of constant T and R coordinates in Schwarzschild or in Kerr. So these are indeed, these spheres depend on two parameters, on T and R. Okay, and of course, if I run the procedure in the particular case of Kerr or in the particular case of Schwarzschild, this procedure, due to the uniqueness, recovers exactly the two-parameter family of spheres of Kerr or Schwarzschild. Okay, so how are these spheres defined? So they are defined by the point is to rely on the point is to define them by fixing well-chosen geometric quantities related in particular to the second fundamental forms, the two null second fundamental forms of the spheres as embedded in the space-time, and the third quantity. So these are well-chosen geometric quantities, and you want them to agree with their Kerr values. This is a simplification. It's in reality there is something you have to be careful with what happens at specific modes. There are some constraints, but roughly this is if you simplify the picture, this is basically the idea. And of course, the difficulty is not the definition; it's rather to prove that these spheres actually exist, of course. And I should mention that also on these spheres, there is we can find an intrinsic definition of angular momentum, and this intrinsic definition of angular momentum will be used is the one that is used. Sorry, let me come back to my previous slide. So when I'm talking about suitable constant M and A, they are actually the angular momentum, the parameter A is the suitable definition, intrinsic definition of angular momentum. And the mass M is also easy to compute, but is the so-called Hawking mass of these spheres. So these spheres come up. Naturally, we can define an intrinsic notion of angular momentum and mass on these spheres. And this is the one we use to set up this parameter A and M. So somehow this slide not only answers the issue of the spheres, but also provides an answer for the definition of the mass and the angular momentum. Okay, so where are these spheres, these GCN, special GCN spheres, where do they take place? Again, in the proof, this is connected to this last slice. Okay, so this last slice where I said this was a fundamental part of the argument, because the last slice completely rigidified. I mean, once you have chosen the last slice, this completely prescribes the space-time. This last slice is a concatenation of these spheres. So remember that you have a 2-parameter family of spheres. Out of these 2-parameter family of spheres, I pick up 1-parameter subfamily of spheres, and I cook up a hypersurface from these spheres. And that's how I get this last slice. Okay, so this is how you track the correct spheres of Kerr, or also Schwarzschild in the particular case of Schwarzschild. Okay, so now let me finish the talk with my last slide, where I want to explain the differences with the new challenges that you have to face in the case of Kerr. Okay, so recall that Schwarzschild is the particular case A is equal to 0. And of course, in the case of Kerr, we do it for small angular momentum. So at first sight, it would seem like it's going to be a perturbation of the proof of Schwarzschild. So I claim that, in fact, there are things that radically change when you move, even for very small angular momentum. And this is due, so this is my first point here, and maybe one of the most important, is the lack of integrability of the principal null frames in Kerr. So let me explain what that means. So again, as I said, one of the main points, if not the main, is to exhibit a triangular structure in the problem. And this triangular structure, if you want, is like when you triangularize the matrix. To make a matrix triangular, you have to choose a special basis. So here it's exactly the same thing. To exhibit this triangular structure, it's not in any frame, it's in a very special frame, a null frame. In other words, you have, instead of, it's a version of the orthogonal frame where instead of having 4 orthogonal vectors, you have 2 orthogonal and 2 null vectors. It's very, very widely used for hyperbolic problems. And these particular null frames in Kerr are non-integrable. So what do I mean with this? An integrable null frame, or if you want a geometric null frame, is one in which the 2 null directions are the generators of ingoing and outgoing null codes. So typically, if you are in Minkowski, if I take dt plus dr and dt minus dr, these are 2 null vectors that are the generators of ingoing and outgoing null codes of Minkowski. So that would be a geometric null frame. It turns out that in Schwarzschild, if you want this special frame that makes things triangular, it's again geometric. It's again tangent. It's again the null directions are generator of the ingoing and outgoing null codes of Schwarzschild. But it's no more true in Kerr. In Kerr, if you want, there are 2 frames, an algebraic one and a geometric one. The geometric one generates null codes. The algebraic one gives you a triangularization of the system. And in Kerr, as soon as A is non-zero, these 2 frames are different. The algebraic frame is non-integrable. It's not the generator of a null cone. There is a rotation. It's due to the fact that things start rotating. The null directions due to the rotation of the black hole, these directions are non-integrable. Okay, and that forces you to really drastically change the approach that is standardly used. The approach since the stability of Minkowski, proved by Christou and Kleiman, is always to use these geometric null frames that span null cones. And here, this is a drastic change in the proof because you have to start learning to work with non-integral gauges. So you first have to define these gauges and be able to control them. Yeah, I guess, can I maybe take a little bit more time? Because I guess my time is 5 minutes.
Yes, please, go ahead, yes.
Yeah, sorry. So this is my last slide already. That's a reassuring thing. Yeah, so I'll take, sorry about that. I'll take 5 more minutes maybe to
Yes, no problem. Go ahead.
So I won't go to all the points, but I want to make some of the points here. Okay, so again, so this required to work with non-integrable gauges. In other words, you have to come up with new constructions that in which the frame is not adapted to the spheres. There are spheres like before, but the frame is not adapted to the spheres. Okay, let me skip the second point. It's important, but I will need too much time if I start. And let me also skip the third point, since it's again connected to these special GCM spheres that I already discussed. So let me talk about the last 2 points, which are in some sense all connected with my first point. So why is the lack of integrality problematic? Why is it? Well, the first problem is the construction makes it's harder. If you constructing a geometric frame is more natural if you want. But besides the construction, what is harder is the type of estimates you want to get. Remember that there are certain type of estimates which are Hodge type systems on spheres, so elliptic systems of spheres, typically difficult systems on two-dimensional spheres. So this system now are problematic because your frame is not adapted to the spheres. So the type of elliptic systems that you get, these are for operators which are not tangent to the spheres, even for small angular momentum, as soon as the angular momentum is non-zero. So here, this is really problematic. You cannot control the system directly. So what you need to do is to construct an integrable structure. In other words, this time a geometric frame, which is adapted to the sphere, and that you compare with a non-integral frame. And then you need a mechanism to go back and forth between the two. In other words, you get an elliptic system in one frame, you translate in an elliptic system in the other frame, plus an extra term, and you have to control the extra term. Then you use the control in the integrable frame, and then you have to go back. Okay, so that's probably the main additional difficulty is the fact that you cannot directly integrate the Hodge type systems if you're not integrable. And now let me mention another difficulty you have to face. So again, remember that there are two types of estimates. There are decay estimates, and there are energy estimates. Decay estimates typically is for low number of derivatives, so you can lose the derivatives there. It's not a problem. But for boundlessness or for top energy, the top derivatives, you're not allowed to lose derivative. So this is another issue because the kind of non-integral frames that we construct that are suitable for decay do lose derivative. So that forces you to work with two types of non-integral frames. One that is suitable for decay, and one that is suitable for not losing derivative. In other words, one is well posed, but is not very good to get decay estimates, and the other one is not well posed, but is good for decay estimates, because for decay estimates you can lose derivative. Okay, so that forces you. So if you count, in fact, the moving from Schwarzschild to Kerr forces you to move with to construct many more objects. In other words, in Schwarzschild, I have exactly one frame that does all. It's integrable, and you don't have to think about these issues. Here, I have to work with three frames: one non-integral frame for decay, one non-integral frame for energy, and one integrable frame to integrate the Hodge type systems. So this is probably the most the part that gives you the most extra work compared to Schwarzschild. Okay, I'll stop here. Thank you very much.